previous lecture we have learnt about rational numbers, whole numbers, natural numbers and integers. In this lecture we will learn more about irrational numbers and their decimal expansions also, the decimal expansions of rational and irrational numbers. So good morning, good afternoon and good evening to everyone who is watching this lecture. Okay, so I hope you like the previous lecture, and if you haven't watched it you can go and watch that, and this is the continuation of that lecture. Okay, so we are following the NCERT book. So in NCERT book this lecture is irrational numbers. Okay, irrational numbers. So what is irrational numbers? I am going to write the definition. Irrational numbers. Okay, irrational number. A number m is said to be irrational if it cannot be expressed in the form of p by q, where p and q are integers and q is not equals to 0. So it's the means the opposite of rational numbers is irrational number. See, a number m is said to be irrational if it cannot be. Okay, the important part is if it cannot be expressed in the form of p by q, where p and q are integers and q is not equals to 0. Okay, so just like rational numbers, there are infinite irrational numbers. Okay, there are infinite irrational numbers. Just like rational numbers, there are infinite irrational numbers in the number line. Okay, so some of the examples that I am going to write, examples, that is root 2, root 3, okay, root 15, then pi, the pi that you use in geometry, that pi. Okay, that is also there. Some decimal numbers I will tell. We will more learn about these decimal numbers, how they are irrational. We will learn more in the next section. But decimal numbers like these. Okay, like these decimal numbers, these are also irrational. The square roots of numbers which are not perfect squares, are irrational. Okay, if the means see 2 is not a perfect square, so it is irrational. Root 3 is not a perfect square, it is irrational. But root 4 is a rational number. Okay, root 4 is a natural number because value of root 4 is 2 or minus 2, whatever it is. Okay, so this square root of perfect squares are rational numbers. Okay, square roots of perfect squares are rational numbers. Okay, so yesterday we had learned the real number line. Okay, yesterday we had learned about the number line. in the number line we depicted, see, in the number line we depicted even rational numbers, irrational numbers, okay, we depicted everything. These number lines contain infinite numbers, okay. These number lines can contain infinite numbers. This is a rational number, this is also a rational number but it's an integer. This is a fraction but it is a rational number. In between two integers you can see you are getting a rational number, okay. Similarly, between these two integers there are infinite irrational numbers also, okay. Like these numbers 0.1, somewhere here this number 0.10, this number exists, okay. These irrational number exists somewhere in between. So how we will find these numbers, okay. And one more thing before we do this, there is a concept. If we know, like we know the rational numbers, okay, rational number set we know, that is denoted by Q, okay. It can contain all the integers, fractional integers, that we know. Okay, we have already seen these yesterday, okay. That we know these rational numbers. If we add irrational numbers to the set of rational numbers, we get what we call it as real numbers, okay. Real numbers denoted by R. What it is? It is a collection of all rational and irrational numbers. See, if all the integers and fractions, they were part of rational numbers. If we include all the decimals which are not which are not rational, they are irrational numbers. If everything you include, all the numbers in the number systems are included in real numbers, except one thing, that is not the scope of class 9th or 10th, it is in 11th, okay. Except that those numbers, those are called complex numbers. Complex numbers are what? These are the square roots. Complex numbers are square roots of negative numbers, okay. So complex numbers are not part of our syllabus. So up until now only we will learn about real numbers. Real numbers are those numbers which can be expressed, which contains both rational and irrational numbers, okay. So this is the definition. And the number line, the real number line also is there. Real number line, if the number line represents rational, like 1/4, okay, 0.6060 like these, okay, then 2, 3 and like so on. If it depicts such, like if it depicts both rational and irrational numbers, if a number line shows both rational and irrational numbers, okay, so it's a real number line. If a number line shows both rational and irrational numbers in it, this is a see, if only it is showing integer, it is an integer number line. If it is showing rational numbers only, so it is a rational number line. If it is showing both rational and irrational numbers, it is a real number line, okay. So here I have said that square root also exists and it can be depicted in number line. So how we will depict those square roots? We will see the example, okay. Example, we locate root 2 on the number line. as I've already said, I will be discussing only the method. Okay, the theory part and everything you have to write. Whatever I am telling, you have to write that in the exam. The same thing you have to write it in the exam also. But I am not writing it because it will take a long time. I am just only telling the method. You have to write it in the exam. Okay, like you have to draw a square. You have to means why you are drawing a square. Everything you have to write that you are doing this and that. You are drawing a square of OABC. You are doing this. Everything you have to write. But I am only mentioning the method. See, how you are getting root 2. How root 2 is calculated, you tell me. Like suppose if you take a triangle or a square, okay, if you take a triangle or a square, let's suppose we take a square and its diagonal, okay, and its diagonal. If the square, we are drawing a square OABC, okay, this is a square. If the square is of unit length, only one unit length, square OABC is of unit length, okay, only one length. By Pythagoras theorem, you know Pythagoras theorem, what it is? Hypotenuse equals to, hypotenuse square equals to what it is? Base square by height square, you know that. Okay, so what is the base? OB square equals to, base is OA square plus height is AB square. What is OB? It is OB square. We don't know the value of OB. We want to find the value of OB. OA is of unit length, we know that, so it's square. AB is of unit length, we know that, it's 1 square. So OB square equals to 2. Okay, so OB equals to what we get? OB equals to root 2. The value of OB we are getting is root 2. You see? So this is how the value root 2 has come into existence. How they found out actually. Okay, the value of root 2 by Pythagoras theorem. Now that same thing, what you do is you make a number line. Okay, there is 0, there is 1, there is 2, there is 3, okay, and so on. This is -1, -2. Likewise it is there. You place this here. Okay, you place this square here. Okay, you place this square here, O A B C, the same square. This is of unit length, this is unit length. Okay, if this is 1, this is root 2. This same square that we have calculated, I am placing here. You see in the number line 0 and 1, this number line is 0, this is 1. So in this square, this root 2 is there. Now what you do is, you have made a circle. How do you make a circle? You put a compass. Okay, compass, and you make a means you know the radius. You measure the radius. Like if you want to make a circle of only 1 centimeter, how you will make? This is the radius. You measure the compass, then you draw a circle. Okay, so we'll make an arc here. What will arc? Draw an arc with OB as the radius and the intersection point of the arc with the number line corresponds to the value root 2. Okay, so what we'll do, we'll make an arc here. We'll draw an arc like a part of a circle. Okay, this arc touches here at point P. This point P value, okay, this point P value is root 2. You are getting it? See, this one is OA is 1, OP or okay, OP is equals to OB is equals to root 2. This value and this value is same. You are drawing a circle, a part of a circle, okay. So these two values are same, that is root 2. So you can see that root 2 lies between 1 and 2. So its value lies between 1 and 2. That you can figure out. Okay. So this is how you are finding the position. This is how you are finding the position of a irrational number on a number line. Okay. There is one more example, similar example. Okay, that I will draw. I will write only the method. Okay, this time example 4, because the second part, that is the decimal expansion part, is long, because the exercises are long there, so we need some more time. Okay, so here it is, locate. Whatever I have discussed, you have to write step by step. See, you have to draw a circle. I would say let OABC be a square of unit length. By Pythagoras theorem, you see OA equals to 1 unit length, AB equals to 1 unit length. So by Pythagoras theorem, this is this. So OB value is root 2. Now in a number line, we plot the same square on point O as point 0 as point O and 1 as point A. Okay, you draw this, then you say that OB, the diagonal is value of root 2. So now we draw an arc with OB as the radius, and it intersects the number line at point P. Okay, point P of the number intersects the number line at point P, and the value of OP is root 2. So OP depicts the position of root 2 in the number line, that you have to write. Okay, now locate root 3 on the number line. Now locate root 3 on the number line. Locate root 3 on the number line. So how you will do? Same method. Okay, you draw a number line, but this time what we will do is, see, 0, we have put 0, then we put 1 and 2, then 3, here similarly minus 1, minus 2. This time we will go for a triangle. Okay, how you are getting root 3? Root 3, see, root 3, you can write root of 2 plus 1. Now this is Pythagoras. So if you go for by Pythagoras theorem, this is root 2 square plus 1 square. Okay, 2 are getting by root 2 square is 2 plus 1 square. So we need a triangle whose base is root 2 and whose height is 1. Okay, how we will get the triangle? We already know that if this is already length 1 unit. Okay, if we draw another triangle of 1 unit length. Okay, if we draw another triangle of 1 unit length, this is also 1 unit length. Okay, so this is root 2, this is A, this is B. So we know OA square plus AB square, okay, equals to OB square. That we know. OA is how much? 1 square. AB is 1 square. It is OB square. So OB square equals to 2. So OB equals to root 2. That we got. Now again what we will do? Again we will draw a triangle of unit length. Okay. This is root 2. This is the height we will draw of unit length. Now this is point C. Okay. Let BC equals to 1 unit of length. Okay. Again by Pythagoras theorem, you put Pythagoras theorem, what it is? OB square plus BC square equals to OC square. What is OB? It is root 2 square plus what is BC? 1 unit. Okay, OC square. So OC square equals to 2 plus 1 equals to 3. Okay, so what you are getting? OC equals to root 3. You got OC equals to root 3 by calculation. Now what you do? See, you draw an arc. Okay, this is the arc you draw. This is point P. Again you draw an arc. Okay, this is point Q. OC equals to root 3 equals to OQ. Okay, OB equals to root 2 equals to OP. How? Same thing, again you draw an arc with OB as the radius. It will intersect the line. It will intersect the number line at point P. That value is root 2. Okay, that value is root 2. But again, this value is root 3. Are you getting it? If you draw a arc with OB as the radius and it intersects at the point P, okay, on the number line, and its value will be root 2, same as OB. If you draw an arc with OC now as the radius, it will intersect the number line at point Q, okay, whose value will be root 3. So root 3 also lies between 1 and 2. This you found out. Okay, on the number line, these are the two examples. That is example 4. Then we will go for exercise. Okay, exercise. This is the second exercise of NCERT. Second exercise. First question is, state whether the following statements are true or false. Justify your answer. Justify. See, I will be writing only the answers and I will tell you what you have to write. Okay, I will not be writing the whole definitions and everything. Every irrational number is a, first question is, every irrational number is a real number. Every irrational number is a real number. Okay, so what will be the answer here? Every irrational number is a real number. The answer is definitely true. See, what real number? What is real number? Real number is a mix of rational numbers. Is a mix of rational numbers plus irrational numbers, or not? That is the definition. Real number is a mix of rational numbers and irrational numbers. So if rational numbers, real number consists both rational and irrational numbers. So definitely every irrational number is a real number, or not? Okay, so this is definitely true. You have to write, like in the exam you have to write, in exam you have to write definition of irrational numbers. Definition of irrational number. Then give example of irrational numbers. Example of irrational numbers. Then write definition of real number. Give example of real number. Include real number. Example of real number include irrational numbers in them. Include irrational numbers in them. Okay, so then you write the statement that yes, since real numbers consist of rational and irrational numbers, hence all the irrational numbers are real numbers. That you can do. Okay, the second question, every print on the number line is of the form every print on the number line is of the form of root m, where m is a natural number. Okay. So it is definitely false. Every print on the number line is of the form m, where m is a natural number. So no, there is no way. Okay, there is no way of getting -1. Okay. There is no way of getting -1. Just let me check. Root m, where m is a natural number, on the number line is of the form root m, where m is the natural number. 0, 1, -1, 2 square is 2. That is a root 3. See, actually, A is false because, see, you can get -1 because the square root of 1 is 1 and -1. Okay, so it is actually false because the square root, okay, the square root of -1 is not represented in the number line. Not represented in the number line because these are complex numbers. Okay, these are complex numbers. The square root of -1 is not represented in the number line because these are complex numbers and cannot be shown on a real number line. Okay, so the value of root 1 -1 is I. Okay, this is a complex number that you will learn in higher schools, that is 11th and 12th you will learn about it, so there is no point, but the above statement is false. Okay, because in a number line the square root of -1 cannot be represented. Okay, then the third question is, every real number is an irrational number. So see, I have already told you, rational number. Real number is a part of real number, consists of rational and irrational numbers. See, real number consists of rational and irrational. So real number consists rational numbers also. So how every irrational number means real number be an irrational number? Okay, so it cannot be. So the answer is false. Okay, so again in exam you write the definition of this irrational number, definition, example, then you have to mention the statement. Okay, this is the way you have to do. Then the second question is, are the square roots of all positive integers irrational? If not, give an example of the square root of a number are the square root of the square root of a number that is a rational number. That is a rational number. Okay. So we know, I have already told you square roots of positive integers or square root of perfect squares. Square root of perfect squares are rational numbers. I have already told you are rational. Square root of perfect squares are rational number. Example is root over 4 is 2, root over 9 is 3. See, this is rational number. No, this can be represented 2 by 1 p q. Okay, this is also can be represented as 3 by 1. Okay, p and q, rational numbers. Rational numbers. Okay, so no is the answer. Then the third question, similar question, no need of doing it again and again, but I will show you. Show how root 5 can be represented on a number line. See, now root 5. Okay, how we are going to write root 5? Root 5 can be written as 4 plus 1. That is what? 2 square plus 1 square. Okay, so this time the number line, what we will do, this is the number line. We are doing 0, then 1, then 2, then 3. Okay, this is minus 1, minus 2. We are doing. So we will take a triangle whose base is of 2 units. Okay, whose base is of 2 units. Base is of 2 units. Height is triangle OAB. Triangle OAB. OA equals to 2. AB equals to 1. So AB equals to 1. Pythagoras theorem we are using. Pythagoras theorem. OB square equals to OA square plus AB square. Okay. OB square what we are having? 2 square plus 1 square. OB square equals to 4 plus 1 equals to 5. So OB is root 5. Okay. So this is root 5. Then again you draw a circle. So it lies between, this is root 5. Okay, this is point P equals to OP is root 5. Okay, root 5 lies between 2 and 3. You can see here, definitely it lies between 2 and 3 in the number line. Okay, so this is the second part. We will straight away go to the third part now. Okay, real number and their decimal expansions. Okay, this is the second part, real number and their decimal expansions. So see, a real number is a fraction like 15 by 2. It's a fraction. It can be fraction, it can be an integer. So if if it is an integer, that means it can be written as a fraction, but it is a divided, means the fraction can be divided, but here it cannot be divided properly. So what we are getting decimal points, 7.5 we are getting real number. So we have to find their decimal expansions of each of the fractions. Okay, and see from why we are learning the decimal expansions, we can distinguish, because we can distinguish between rational numbers rational numbers and irrational numbers by looking at their decimal expansions. Okay, by looking at their decimal expansions. See, these decimal expansions of real and irrational numbers have certain properties. Okay, have certain properties. From those properties we can infer that whether that number, that decimal number, is a real number or a is a irrational number or a irrational numbers. Okay, so we'll go by examples. So we are having an example. See, let's see, this is example 5. Okay, go by example, like we will find those properties by example. Okay, so it is been shown, three fractions are given. Find the decimal expansions. Find the decimal expansions of 10 by 3, 7 by 8 and 1 by 7. See, these three fractions are there. We have to find the decimal expansions. So how you are going to find the decimal expansions? The same way, like in childhood that you used to do divisions, same thing. You do divisions like childhood. Okay, 3, you keep here 10. By how many times 3 will go? 3 times will go. You write 3. You gave 3. 1 came remainder. Now with 1 you cannot do the division. So what you will do? You will put a decimal, add a 0. Okay. So then again you got this 10. Again you got 10. Sorry. This is 9. 3 times if you do, this is 9. Okay. Same thing. This is 9. Okay. 3 into 3 is 9. So 1 is remainder. Then you put a decimal. You did added a 0. Then again 3 into 3 it is 9. After decimal. Okay. Again you got a 0. So this thing keeps repeating. Again 3 into 3 times is 9. Okay. Again. So the remainder is remainder. The remainder every time it is 1 only. Every time, see, this remainder it is 1. This remainder is 1. Every time the remainder is 1. Okay. What is the divisor? What is the divisor? It is 3. Understood? This is the divisor. This is the quotient. Okay. Similarly, you do it for what? 8. 7 by 8. Okay. You do the division of 7 by 8. Now you see, by 7 it will not go. You cannot do. So what you will do? You will put a decimal point. You will put a decimal point. 8 times it goes. It is 8 into 8, 64. So what is the remainder? 6. Again it cannot go. So you will, what you will do? You will put a 0. Okay. This will go by how many times? It will go by 7 times. Okay. 60. This is 56. Okay. 7 times 56. Then 4. You put a 0 again. 5 with 5 it goes 40. Okay. So the remainder comes 0. So the string of remainders that you are getting is, what you are getting? 6, 4 and 0 you are getting. String of remainders that you are getting is 6, 4, 0. And what is the divisor? What is the divisor? That is 8. Okay. Now see, we will do 1 by 7. This is 7, 1. You cannot do the division, so you will put a decimal and add a 0. 1, 7, and 3 is the remainder. Okay, we will add a 0. 30, 4 times, 28. 2 is the remainder. 20, 2 times, 14. 6 is the remainder. 60. Okay, so 8 times, 56. Again 4 is the remainder. 40, 5, 35. Okay, 5 is the remainder. 50. Okay, 7, 49. 1 is the remainder. Again see, remainder is remainder. String of remainders I am writing. See, this is 3, this is 2, this is 6, 4, 5, 1. String of remainders is 3, 2, 6, 4, 5 and 1. Okay, this is the string of remainders. Then the divisor is 7. Okay, remainder is 3, 2, 6, 4, 5, 1. Divisor is 7. So what you are seeing, you can see, you can infer 2 or 3 things from these divisions. Okay, you know what you can tell. 10 by 3, 10 by 3, these numbers 10 by 3, we are given 7 by 8 and 1 by 7. These are what? These are rational numbers. Rational numbers, definitely it can be seen that p by q form is there. So these are rational numbers. Okay, in the decimal expansion, what you are seeing is, in rational numbers, what you are getting, the remainder either terminates to 0, or after certain digits the same thing this in pattern repeats. See, like here, see, this is the most clear cut example. See, you got so many remainders, again you got 1. So if you add a 0, same thing will repeat again same thing will repeat. The 6 steps, 1, 2, 3, 4, 5, 6 steps you will do, again you will get 1. So this quotient that is 1, 4, 2, 8, 5, 7, again it will repeat. If you write the number, if you increase the number, the quotient will be like this: 8, 5, 7, then again it will be 1, 4, 2, 8, 5, 7, then again it will be 1, 4, 2, 8, 5, 7. It will continue, keep on repeating. Okay, similarly here, remainder 1, 1, 1, 1, 1, it is keep on repeating. The quotient after decimal place 3, 3, 3, 3, it is repeating, it keep on repeating. Okay, or it is either the string is repeating or it is terminating at 0. You see this thing, 8 is there, so 0.875. okay, this does not repeat. Okay, it terminates once the remainder comes as 0. Okay, so there are these 2-3 properties. Okay, so what are the properties? I'm writing, what are the inference, you can say, the inference from this, you can say the remainder either become 0 or start repeating themselves after certain stage. Okay, remainder either become 0 or start repeating themselves after certain stage. So this is one thing you are saying, that remainder either becomes 0 or it starts repeating, like it will, this thing again it will come to 3, 2, 6, 4, 5, 1. Okay, this remainder will start repeating themselves after certain stage. Okay, the second thing that you noticed, the number of entries in the repeating number of remainders is less than the divisor. The second thing what you noticed is, see, the number of remainders, the maximum is divisor is 7. Okay, so the repeating strings is less than the divisor is 7. You will get maximum only 6 remainders that will be unique. Okay, the number of repeating, the number of entries in the repeating string of remainders, in the repeating string of remainders. See, this is a question in the exercise also, that is why this point is very important. See, if it is a rational number, okay, so the maximum number of means the digits, maximum number of remainders that can happen is 1 less than the divisor, that it can happen. See, it is always less than the divisor. It can be 1. If the divisor is 7, it can be 1 only divisor, 1 remainder, 2 remainder, 3, 4, 5 and 6 remainders. Okay, maximum it can be 6 remainders, okay, that are repeating. The number of entries in the repeating remainder is less than the divisor. This is a question also I will show you in the exercise. Okay, the third inference that we are getting is, if the remainders are repeating, the quotients are also repeating in a pattern. Okay, if the remainders are repeating in a pattern, the quotients will also repeat in a pattern, because you see, remainder, if you are getting that same quotient also will multiply with the same numbers, no? So the quotient will also be repeating. So if remainders repeat, then we get a repeating block of digits in the quotient. We get a repeating block of digits in the quotient. Okay, so what properties are there? So we can say, this is a note. Okay, this is a note that I am writing. We can write that rational numbers have a property. Rational numbers have a property where the remainder either becomes zero, or the remainder remainders repeat in a pattern. Okay, so we can say, you can see that there are two properties that we have inferred, that whether either the remainder will become zero or it will repeat in a pattern. Okay, so the first case is the remainder becomes zero. The remainder becomes zero. Okay, so the remainder becomes zero. That was the first case. Okay, the example where the remainder becomes zero is 7/8. Okay, see, this is, I will not discuss it again also. See, this is a property also, when in which numbers, on certain numbers only it will become, the remainder will become zero. In which numbers it will become zero? You see the example I am writing, 1/2. Okay, 0.5. 1/5, 0.2. 1/10, 0.1. 1/4, 0.25. See, here the remainder is becoming zero. In which case, what you can infer is, see, this is 1/10, you can write as 1 into 2.5. Sorry, 2 into 5. This one you can write as 1 into 2 into 2. Okay, you are seeing this, 1/8 also. 1/8 also, this is what you can write, 2 into 2. Okay, so this is a pattern. So the remainder of rational number becomes, a very important point, becomes zero if the denominator is of the following pattern. There is 2 to the power m into 5 to the power n, where m and n are in integers. M and n are integers. Okay, 2 to the power m into 5 to the power n, where m and n are integers. Only where in these situations only you can get the remainder as 0. Otherwise you will not get any other number, you will not going to get the remainder as 0. only the numbers where the factors are 2 to the power m into 5 to the power n. Okay, only in those numbers you are going to get the remainder as 0. Okay, if the remainder becomes 0, then the division has finite number of steps. Okay, and we can say that the decimal expansion, see here the decimal expansion is finite, so it is getting terminated. So we write that if remainder becomes 0, then the quotient is finite, see this is finite, it is not going to infinity. Okay, infinite number of digits are not there. There is a finite quotient, and the decimal expansion is said to be terminating. Okay, is said to be terminating. This is the important point, because I will address whether a number is rational or irrational based on these only, terminating, whether the decimal expansion is terminating. When the decimal expansion will be terminating, when the remainder becomes 0. Okay, if the remainder becomes 0, that means the quotient is finite. You will get a finite quotient. Okay, see, when you are getting a finite quotient, when the remainder will become 0, every time you will multiply, what will you get? You will get 0. After these zeros are only there. Okay, so you are getting a finite quotient. So when the remainder becomes 0, you are getting a finite quotient, and you say that the decimal expansion is a terminating one. Okay, because it terminates there. The second case, okay, case 2. Two types of cases were there. Case 2, the remainder never becomes 0. The remainder never becomes 0. Okay, if the remainder never becomes 0, in this case what we say? In this case we say the decimal expansion is non-terminating repeating. Okay, is non-terminating recurring expansion. Recurring, let me write it in non-terminating is non-terminating recurring. Okay, what we mean by that is, see, it will never end. The decimal expansion will never end in these cases where the remainder never goes to 0. The decimal expansion will never end. Here. Okay, but it will be recurring. Every time the decimal expansion will have a same pattern. Okay, so the decimal expansion is non-terminating and recurring. That is what we are writing. Okay, and how we are going to express it? How you are going to express these recurring numbers? You see, like if this is the number, no, you can write it as a bar. The recurring part you can keep it under a bar. Okay, so if it is like this 3 5 7 2 7 2, after a digit, or if it is recurring, then also you can write it, see, like 5 7 2. Only keep this part as in the bar. Okay, so the part which is recurring, you have to keep that part in the bar to show that it is recurring and it is a short form. Okay, so what is the definition? We can say is, if a decimal expansion of a number is terminating or is terminating or is non-terminating recurring, we can conclude it to be a rational number or not. We got only two properties. Either see if the remainder becomes 0, so if the remainder becomes 0, so the quotient is finite, and what happens is the decimal expansion is terminating. It stops after some digits. But if the remainder never becomes 0 and the remainder has a pattern, okay, if the remainder never becomes 0 but the remainder has a pattern, a string of digits in a pattern, okay, so the quotient is infinite but the quotient will repeat in a pattern. Okay, so we tell that the decimal expansion is non-terminating recurring. So if a decimal expansion is terminating or not terminating recurring, either of them, then we say that it is a rational number. Okay, so what will be an irrational number? You say, what be an irrational number? What be an irrational number? If a decimal expansion of a number is non-terminating, non-recurring, we conclude it to be a irrational number. Understood? See, if it was terminating or if it was not terminating but it was recurring, it was a rational number. But if it is not terminating but it is not recurring also, there is no pattern in the quotient or the remainder, you can say, because if remainder has pattern, the quotient will also have a pattern. Okay, if the both does not have any pattern, so it is non-terminating also, it is non-recurring also, so it is an irrational number. Okay, so some examples we can give. That is root 2 by method. I will show you the method in some other chapter. This is 1.14142. See, this is not recurring and it will never recur also. Pi also likewise 3141. Okay, and sometimes in geometry you have seen we write pi as 22 by 7. It is actually wrong. It is approximately equal to, pi is approximately equals to 7. It is not equals to 22 by 7. Okay, it is approximately. To ease our calculation, we do that pi is 22 by 7. Pi is a irrational number. It is not equals to 22 by 7. If it was 22 by 7, it would have been a rational number. But it is an irrational number. So, it is 22 by 7. Okay. So, what we will do? We will go for examples now. Okay. Example 6. What the question is? Show that. I will show that 3.142678 is a rational number. See, these questions will never be asked in an exam. If it is asked, it is for 1 mark only. There cannot be more than that. Okay, show that. See, this number, it is neither recurring, nothing, but it is finite. You can say, you have to write the decimal expansion of this number. The decimal expansion of this number is finite. So that is one property of rational number. So rational. Okay. The second thing is, you can in fractional form 2678 by 13 fractional form. Okay, fraction, this is p, this is q, integers, so rational. So it is a rational number. You got it? Understood? Okay, so two methods are there, both you have to do actually. Okay, then example 7, show that 0.3333 and on is 0.3 can be expressed in the form of P by Q, where, see, this question will be repeating. Okay, 2-3 types are there, this question will be repeating. So where P and Q are integers and Q is not equals to 0. Okay, so this is one. So how you will do? So see, what we will do is we'll take this number. Let us take 0.333 equals to x, or take, or you write assume. Okay, assume this is at x. Okay, if that is x, so x equals to 0.3 definitely. Now multiply by 10. See, this 10 I am mentioning, or I am telling you already. Why multiply by 10? Why multiply by 10? See, only if one digit is repeating, one digit recurring, not repeating, recurring I am writing. If one digit is recurring, multiply by 10. Multiply by 10. If two digit recurring, multiply by 100. Multiply by 100. Okay. If one digit is recurring, multiply by 10. If two digit recurring, if three digit is recurring, multiply by 1000. Okay. Why, you will see. If I multiply by 10, it becomes 10x, and this thing, what it will become? It will become 3.3333 and so on. So what you can write as 10x? This 333 you can write as 3 plus 0.3333 and so on. You can write. You know that x is this. This is x only. So this is 10x. Okay. 10x equals to 3 plus x. So what you are getting? 10x minus x equals to 3. So this is 9x equals to 3. So this gives x equals to 1 by 3. Understood? So we got the value of x as 1 by 3. So 0.3333 and so on. It is 0.3 is fractional value is 1 by 3. So this is the method that you will be doing. We will see more examples of it. Example 8. Okay. Show that 1.272727, that is two digits are recurring here, can be expressed in the form of P by Q, where P and Q are integers and Q is not equals to 0. Understood? See, same thing. Let us assume this repeating number 2727 and equals to x. Okay, since it is two digits, multiply by 100. Since two digits are repeating, so if you multiply by them, this becomes 10x equals to what it will become? 127.2727 and so on. Okay, so what you can write as 10x. Now you see, we need this number again, that x we need it. So how many times we means how we'll get this? If we write it as 126 plus 1.272727. Okay, you understood this part. I'll get 127.272727. 126 plus 1.272727. Okay, so now this is x. So this becomes 10x equals to 126 plus x. So this becomes 10x minus x equals to 126. So 9x equals to 126. So x equals to 126 by sorry, very sorry, this is not 10x, this is 100x. Okay, we had multiplied by 100x. Okay, so this is 99x, this is 99. Okay, sorry, this is 99. So x is 126 by 99. So we found the value of 1.272727 and so on as 126 by 99. So this is the rational number, okay, of whose decimal expansion is 1 to 1272727. Okay, next example, same example is example 9. Okay, show that 0.2353535. See, there is a digit 2, then the repeating starts. Okay, so 0.235 can be expressed in the form of P and Q, in the form of P by Q, where P and Q are integers and Q not equals to 0. Okay, so same thing again we have to do. Let us take 0.23535 and so on equals to x. Okay, since two digits are repeating, multiply by 100. Since two digits are repeating. Okay, so what it will be? We multiply by 100, that will become 100x equals to 100x. This will become how much? 2.35. Okay, sorry, this will become 23.53535 and so on. So to get that pattern again, what we will do? 100x equals to, we need how much? 0.23535. If we take out 2.3.3, so we'll get this number again, 2.23535. This pattern you will be getting 23.3. Okay, you just do you minus this part. If you do the minus from this to the 23.53 minus this, you will get this 23.3. Okay, so you do the minus 23.3 you are getting. So this is x. Okay, so this becomes 99x equals to 23.3. So x how much it is? 23.3 by 99, that is 233 by 990. Okay, this is the value of x. So the decimal 0.23535 and so on. The rational number is 233 by 990. Understood? So this is example. Then example 10. Here earlier we are finding the rational numbers between two numbers. Okay, in earlier exercises we are finding rational numbers between two numbers. Here we will find rational numbers. Find an irrational number between 1 by 7 and 2 by 7. Okay, So how we will do it? 1 by 7, same we have to do. 7 1 0 0.17 30. You do the division. Okay, see, these are rational numbers, so it will have a either a terminating or a non-terminating recurring decimal expansion. Okay, so you do the expansion part. 20 2 14 60, okay, 8 56 40 5 35 50, then 7 49, again is 1. So this is the repeating part. Okay, 1 by 7 you can write it as 14285 7. Okay, similarly 2 by 7 you do 7 2. Okay, so shall again see, there is an example, there is a question in exercise also, so I will tell you the easy part. You do in exam, again you do the quotient part. Okay, but I will tell you how to do it. See, 1 by 7 you are getting 1 by 7 you are getting as 0.142857. This is the expansion. Okay, 2 by 7 you can write it as 2 into 1 by 7 or not. Okay, so 2 into the same thing you can multiply the repeating part. So what you can do is you multiply this 14 11 1 16 17 1 5 8 2. See, this is 2 by 7s, 0.285714. If you do the, let me do it again, because in the exercise it will come a question, so you need to be clear. See, 2 by 7, no, 7 2. Okay, you cannot divide, so decimal 20 2 14 60. Okay, here it will 8 56 40. Okay, 35 you will be getting 50. 35 is 5 50 49, it is 7. Okay, 1 10, that is 1 7 30 4 28 2. See, again 2 came. You are getting it or not? This thing 2 by 7 to 0.28574. So it's better you use this trick. See, this is a decimal expansion of 1 by 7. So you use this trick, multiply it into 2, the same thing. So you'll get the decimal expansion of the 2 by 7. Okay, similarly 3 by 7 you can do, 4 by 7 you can do that. Okay, so what we have to, the question was to find an irrational number. So see, the decimal number you have got is, these are the two numbers. You have to find an irrational numbers. You have to find an irrational number between these two. See, simple irrational number is you do not need to repeat a pattern. Okay, in a decimal number you do not need to repeat a pattern. So if it is terminating, then it is a rational number. If it is non terminating, so this should not have any pattern. So how it will not have any pattern? This way. See, this is 0.14, this is 0.2. So you take 20, then again 200, then 200, then 240, and so on. Okay, so here the pattern is never repeating. Why it will never repeat? See, this number here, see here 2 it is coming. If you divide it again 20, you will get 14. So same thing will repeat, but here it is not repeating. So no way by division method you will get this number. It is somewhere, it is the square root of some number. Okay, so no way by division method you will be getting this number, this decimal number. Okay, that is why it is an irrational number. So this is the method only that you can do. Okay, so this is then we will move on to the exercise. The video has been becoming too long. Okay, it's more than an hour now. This is the third exercise. This is not exercise, sorry. Exercise 1.3. Okay, so I'll means do the questions fast, and I will explain it only. I will not write the means I will write the gist only. I will not write the entire steps. Okay, write the following. In the exam, you have to write the entire steps. As I have said in every time I am saying it, in exams you have to write all these steps. But now, for explaining purpose, I am writing only the important parts. Okay, write the following in decimal form, and what kind of decimal expansion, and what kind of decimal expansion. What kind of decimal? There are three types of decimal expansion. Either it is terminating, or it is non-terminating recurring, or it is not terminating not recurring also, non-recurring also. Okay, so first question is given 36 by 100. Okay, you know I will not do the division part. This is 0.36. Division part you can do. One only I am doing for your sake. Okay, 36, this is 100. It cannot go decimal. You give 3. So this is 300. Okay, 360, 600, 6, 600. So remainder is 0. Okay, remainder came 0. If remainder is 0, decimal expansion is terminating. Decimal expansion is terminating. As you can see also, is terminating. Okay, as you can see, it is terminating because the quotient is finite. Okay, then second question is 1 by 11. Okay, 1 by 11. So 1 by 11 if you do, it is going to come as 1 by 11. So it will not go 1 0. It is not going, not getting divided. So one more 0, 100, then 9, 99. Again remainder is 1. Okay, so this thing will keep on repeating. 99, 09, 1. Okay, so the remainder 1 is repeating, or the quotient 1 is repeating. Okay, so it is a non-terminating recurring. By seeing the number also you can write what type of decimal expansion you are going to get, because decimal expansion, see here it was terminating because 100 is in the form I have already said 2m into 5 cube n, where m and n are integers. This is how much? You tell me. This one, this is a factor. Okay, 5 square into 2 square, 2 square into 5 square gives 100. Okay, so this is in this form, that is why it is terminating. Okay, here it is not in that form, so it is not terminating. Okay, and what was the question? We have to find in decimal form. In decimal form, 1 by 11 we can write it 0.09. This is a decimal form. Okay, third question. There are many questions. There are total 9 questions here. Okay, 4 1 by 8. Okay, so you can write it as 4 plus 1 by 8. So that is 32 plus 1 by 8, 33 by 8. Okay, so I am not doing the division. The division will come as 4.125. Okay, this is 4.125. Since it is co-occurred, is terminating. Finite quotient, terminating decimal expansion. Terminating decimal expansion. Okay, finite quotient. You let me know. See, these things are repeating. That is why I am not giving it much time, because your time only will be wasted. You have to practice it. These things I am writing it quickly. If I do it slow, your time will be wasted in watching the video. Okay, the important part I have explained only beforehand. When you are going to practice the exercise, you give your time there and see if you are able to do it or not. Then again, if you are not there, you can write it in the comment section. I will answer the queries and everything. Okay, and if you write it in a future video also, I can answer. I will make a video for the queries itself. Based on these videos, I will make another video on the queries itself only. Okay, 3 by 13. So 3 by 13, it is coming the repeating part. 3 by 13, the repeating string it is coming as 0.230769. Okay, this is the repeating. This is a non-terminating recurring. Okay, see, this is not in the form of 2m into 5n. Okay, so it will be non-terminating recurring only. Then fifth question is 2 by 11. Same thing 2 by 11. Okay, 2 by 11, the repeating part is 0.18. It is non-terminating recurring. Okay, non-terminating recurring. See, 2 by 11, one other 1 by 11 we had already found it as 0.09. 1 by 11 we had already found it 0.09. So 2 by 11 is 2 into 1 by 11. So 2 into 0.09 equals to 0.18. Understood? So that is one another. Then 5 is gone. Sixth is 329 by 400. You can see this is in the form of 2m into 5m. Okay, so it is the terminating one. Okay, but you have to do the division, and the division is coming as 320 by 400. The division is coming as 0.8225. Okay, so it's a terminating decimal expansion. Okay, so this was the first question. Second question is same thing. It is given that 1 by 7 equals to 0.8. The decimal expansion is given. It is told find decimal expansion of 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7. Okay, without division. So I have already told you before, and in the one of the examples, see, if 1 by 7 is there, if 1 by 7 is there and it's is 857. Okay, so what you can write 2 by 7 equals to 2 into 1 by 7. You can write it. So 2 into 0.142857. So it is coming as, okay, so this thing is coming as 0.285714. Okay, you just multiply. You multiply 2 into this number, you multiply, you will be getting it. Okay, 3 by 7 similarly, 3 into 1 by 7 equals to 3 into 0.142857. So you are getting it as, when you multiply, you are getting it as 428571. Okay, 4 by 7 similarly, 4 into 1 by 7, 4 into 0.142857. Okay, so this one you are getting as 571428. It is also said to do it via division to check. Okay, you will be getting this value as I have showed you earlier also. So to save your time and my time also, because the video will be too long otherwise. Okay, 0.142857. So here the value will be 0.714285. Okay, if you multiply, you will be getting these numbers. 7 equals to 6 into 1 by 7 equals to 6 into 0.142857. Here you are getting 0.857142. Okay, so this is if you know, and if it is a multiplication of that number, okay, so easily you can find the recurring decimal expansion, okay, of that number by just multiplying it. Now we'll go to the third question. What is the third question? Express, similar example, express the following in the form of P by Q, where P and Q are integers and Q not equals to 0. Okay, same thing that we have done in in the examples. Okay, it is given 0.6. I am writing only the steps. Okay, 0.6, since only one digit is repeating, multiply by 10. Multiply by 10. 0.6 equals to x. Okay, multiplying by 10 equals to 6.66. 0.6. Okay, so this is, so 0.6 equals to 6 plus 0.6 you can write. So this is x again. So this is 10x equals to 6 plus x. So this is 9x equals to 6. So x equals to 2 by 3. Okay, 6 by 9. Okay. So 0.6 bar is 2 by 3. Okay, understood? The second question is 0.47. 0.47. Okay, 0.47. So again take 0.47, multiply by 100. Multiply by 100. You will be getting 100x equals to 47.47. Okay, so this is 100x equals to, okay, no, so the question is a bit, I have written the wrong question. Okay, so this is only the 7 is repeating. Okay, only the 7 is repeating. If only the 7 is repeating, you have to multiply by 10. You have to multiply by 10. Okay, you have to multiply by 10. 10x, and this one will be 4.7. 47. This will be, sorry, not 47. This will be 77. Okay, sorry. So many mistakes are happening. Okay, so how we need this one? So we will 4.3. If you minus 4.3, you will be getting this number 4.477. Okay, so this is an x. This is x. So this is 10x minus x equals to 4.3. So 9x equals to 4.3. So x equals to 4.3 by 9 equals to 43 by 90. Understood? See, so many mistakes were there. So again I am telling you, so only, see, 4 was not repeating, only 7 was repeating. Since only single digit is repeating, we are multiplying by 10. If you multiply by 10, we are getting 4.7777. It is getting, we are getting this number. Okay, so to get this number, we will minus this 4.7 minus 0.47 we will do. We will be getting 4.77. To get this 4.3, how will do you know? 4.77, 0.47. What are you getting? 4.3. Okay, so you put this 4.3 here. Okay, then you will get 0.47777 you will getting. So this is x. So 9x 4 equals to 4.3. So x equals to 4.3. So the you understood this question. Then the third question. Third question is x equals to, sorry, x now. This is 0.001. These whole three numbers are repeating. So we'll let x equals to 0.001. Okay. If x equals to 0.001, multiply by 1000 because 3 digits are there. Multiply by 1000. Okay, so it is 1000x equals to 1.001. Okay, this thing is repeating again. So how we can write? We can write 1000x equals to 1 plus 0.001. Okay, so this is x again. So this becomes 1000x minus x equals to 1. So this becomes x equals to 1 by 999. Understood? Clear? since there are 3 digits repeating, so we will multiply by 1000. How many digits are repeating? You multiply the means 10 into the number of digits, number of zeros. Okay, if 2 digits 100, if 10 to the power m, number of digits repeating, where m is the number of digits repeating, okay, 10 to the power m is the number of digits repeating. If 2 digits repeating, 100, 3 digits 1000. Okay, understood. We'll go for the fourth question. Fourth question is written as express 0.9999 in the form. It is a very good question. Okay, form of p by q. See how you will be surprised. Okay, same thing we will do. We'll take x equals to 0.9. Same thing we are going to do. Okay, then multiply, since one digit is repeating, multiply by 10 we will do. Okay, multiply by 10, so this will become 10x equals to 9.9. Understood? So this we can write as 9 plus 0.9. Okay, so this is again x, so this becomes 10x minus x equals to 9. So this is 9x equals to 9, so x equals to 1. So how does 9999 equals to 1? Can you tell? So this is also a concept that you will learn in higher classes of limits. See this number, no, 9999, it is repeating. Okay, this thing is repeating, it is approaching to 1. So it is approximately equals to 1. Okay, you learn it in higher classes, that is 11th and 12th. You will learn about limits, so there you will learn. Okay, so this was a good question, then and an interesting question also. Okay, so the fifth question. The next questions are basically, I can say only the last question is good. These questions are basically I have already discussed. See, the question is, what can be the maximum number of digits? What can be the maximum number of digits in the repeating block of digits, in the decimal expansion of 1 by 17. Okay, perform the division. It is also said to perform the division. See, perform the division, which I will not be doing. Okay, perform the division to check your number, to check your answer. Okay, I have already said it. Maximum number of digits in the repeating block. Maximum number of digits in the repeating block is 1 less than the divisor. Because the number of digits should be less than, in the repeating block should be less than the divisor. Okay, divisor is 17. So maximum number of digits in repeating block. I have already said you this. You have seen from the property in the first, the fractions that we have discussed of how to find the decimal expansions, and we are inference. From the inference part I have already said it. You can go and check there. Number of digits in the repeating block equals to 17 minus 1, that is 16. And if you will do the division also, I am writing it directly. Okay, 1 by 17, it is coming as 0.0588 235 294 117 647. This is the repeating block. Okay, if you divide, you will get this, and this will be a waste of your time also, my time also, because in the exam it will not come. 17 times if you do this, you will be going on dividing, multiplying. So most probably it will not come. Okay, sixth question. Look at the several examples. Okay, same, I have already mentioned it. Look at the several examples of rational numbers. Several examples of rational numbers. Look at the several examples of rational numbers in the form of p by q, q not equals to 0, where p and q are integers with no common factor, other than 1, and having terminal decimal representation. Having terminal means it is getting terminated. Having terminal decimal expansion. It is told, can you guess what property must it satisfy? Can you guess what property must it satisfy? I have already told you, this is the property, that the denominator, that is q, should be of the form 2 की power m into 5 की power n, where m and n are integers. If the denominator is of this form, these factors are only 2 and 5. Okay, other than 1 only 2 and 5 are there. Other than 1 only 2 and 5 are the factors, then only the decimal expansion will be terminating. The answer to this is written there also, because I have already shown the examples of 1 by 4, 1 by 2 I have done and written. Okay, so there you can check on the decimal expansion. If you have maintained notes, there you can see where I have shown this. Okay, will be terminating. Okay, this is the 6th question. 3 more questions are there. 7th. Okay, 7th is write, this is useless, write 3 number whose decimal expansions are non-terminating, non-recurring. See, decimal expansion is non-terminating, non-recurring. This means you have to write irrational numbers. 3 irrational numbers, 3 irrational numbers, root 2, root 3, pi. Okay, done. You have to say that non-terminating, non-recurring means the number, if the decimal expansion is this, that means the number is an irrational number. So what? We have to write 3 irrational numbers. Okay, you have to mention that. If the question comes like this, the invigilator wants to know why. You can write a number, decimal number, that is non-terminating, non-recurring, but you are not a class 5 children. Okay, the person wants to know why, what is the property, whose numbers property is non-terminating, non-recurring. Okay, that is why it might have asked this question. Find 3 different irrational numbers. This is shown in the examples also. Okay, between rational numbers, the method I have shown in examples, rational numbers 5 by 7 and 9 by 11. So what you will do, if you want to find a irrational number between 2 irrational numbers, you find the decimal expansion. Okay, between the decimal expansions you get a digit and you put the zeros, like I will show you. See, the decimal expansion of 5 by 7, I will not do the decimal expansion again. Okay, I have done it multiple times. 5 by 7, it is coming as 0.7 71425, 714,285. Okay, this is the decimal expansion, and of 9 by 11 it is coming as 0.81. Okay, this is 71, this is 81. What you can do? You can do is you can do 0.75. Similar, 0.75. Okay, then 755 and 7555. Understood? This is one. Then 78 you can do, 788, 7888. You choose this between these two decimal numbers. You put a decimal number, then the second number you go on increasing one time, one at a time. Okay, this is 80, 8000, 8000. Okay, and so on. These are three irrational numbers between these two rational numbers. Okay, then the ninth question. Here also I will be writing directly. Okay, the question is, classify the following numbers. Classify the following numbers. Classify the following numbers. Following numbers as rational or irrational. Following numbers as rational or irrational. Okay, so the first question, I'm writing the questions and write answers. I will write 5 numbers are there, I think. Okay, 3, 4, 5. First is root 23. This is root 225. This is not root. This is 0.3796. This is 0. This is 7.478478. Okay, then this is 0 1 1 0 1 0 0 0 1 0 1 0 0, 4 zeros, then 1. Okay, so see, the first question is root 23. Square root of not a perfect square. Square root of not a perfect square, what I have said, it will be irrational. Okay, then square root of perfect square. Root 225 equals to 15. So it is rational. Okay, it is irrational, it is rational. This one is terminating decimal expansion. So it is rational. Okay, this one 7478. This is non-terminating recurring decimal expansion. So this is also rational. Okay, here this is what? Non-terminating. This is non-terminating, non-recurring decimal expansion. Okay, so this is irrational. You understood? This is root 23. I have already said square root of not a perfect square is irrational. If it is a square root of a perfect square, so it is rational. If it is terminating, okay, 0.3796, this is a terminating decimal expansion, it is rational. This one is a non-terminating recurring. See, 478 is continuing and it will go on continuing. Okay, it will go on continuing. So it is a non-terminating recurring decimal expansion. We know that it is a property of rational numbers. Here it is not terminating and it is not recurring also. Okay, so it is a property of irrational numbers. So this was the second and the third portion of the number system. Okay, so we'll look into the fourth portion in the next video. Until then, I thank you for your patience, for listening to the chapter, and if you have any queries, you write it in the comment section. Mention what you like and what you do not like about this and what you want me to improve in the future videos also. And thank you for listening to the chapter, and till then, a very good day and stay safe. Thank you again.